This is a sample presentation of the seminar Understanding Combustion and Emission of Pollutants in Engines. The topics we will discuss, first I'm going to talk about the objective of this course and presentation style. Then we talk about fuel, air, combustion, thermodynamics, which in the context of first law of thermodynamics, energy balance on engine, and issues such as equilibrium calculations of pollutants and so on. Then we go to combustion chemistry, where reaction rates and issues pertaining to that are discussed. Armed with this information, then we talk about autoignition. Autoignition is very important. For a spark-ignited homogeneous charge engine, at all costs we would like to prevent it, because that would essentially lead to what we call knock, which is the subject here. If you are diesel engineer, you would like to enhance it, because the whole basic principal operation of diesel engine is based on autoignition. So therefore this subject is extremely important for both spark-ignited and diesel engineers. Then we talk about knock in engines, spark-ignited engine, flame propagation and burning speed. Now, in a homogeneous charge spark-ignited, flame is an important mechanism that essentially burns the fuel and releases the energy. We're going to talk about that, what the flame is, the mechanism of its propagation, factors that affect the burning rate, and so on, and impact on combustion, performance, and emission. Then we talk about the combustion in the spark-ignited engine. After this, we will get into emission of major pollutants that are regulated, such as nitric oxide, unburned hydrocarbons, CO and CO2. After this, we will discuss the effects of some parameters, design and operating conditions, on emissions, and simultaneously we will look at impact of these parameters on performance and efficiency. Then we get into after treatment, catalytic conversion of the pollutants that ends up into the exhaust system. Next is going to be engine technologies for low emissions, and then sensor technologies for engines and for research. And last is going to be some optical diagnostics for engine R&D. Here's a copyright, essentially a slide that tells you limitation in terms of how we could use this information. The objective is really to present sufficient information on combustion emission of pollutants for spark-ignited engines in order to elevate your background knowledge for intelligent application and comfortable understanding of the existing body of knowledge. So the application and ease of access to the all the vast amount of literature that are available are the key thing. So all of this knowledge should be used for your application. So the course is about understanding. It's also about combustion and emission, and every time we'll talk about combustion, the emission and combustion is so intertwined that essentially we'll talk about emission as well. So, understanding, so therefore combustion and underlying reasons and origin of regulated emissions of pollutants are important. In order to fully appreciate and understand that, we need sufficient background on combustion fundamentals, so which we will cover here, some basic terminology. It's only really through such a foundation that one can comfortably understand and grasp the causes of pollutants formation and the effects of the design on operating parameters. The presentation style is going to be more physical and intuitional than mathematical analysis. So mathematical analysis is brought down to minimum. Concepts are immediately related to applications so that you're not left in vacuum as discussions of things in theory and with no applications. And the slide contents are also often dense and not telegraphing, is purposely because you could always go back to this and it reminds you as to what the subject was. There are some key combustion concept ideas that are critical to understanding combustion and emission, of course. And these are laid down here. For example, we're going to talk about distillation curve for fuels and its importance. We want to talk about distinction between overall air-fuel ratio and cylinder-based or local air-fuel ratio. Black box operation of the oxygen sensor and its purpose, to understand. And you understand what the equivalence ratio or lambda is. Adiabatic flame temperature is physical meaning and importance, heating value. Terms such as combustion efficiency, which addresses the combustion efficiency itself than the entire efficiency, because there are several efficiencies in engine. The concept of equilibrium and chemical kinetics, mechanism of overall reaction, the nature of heterogeneous catalytic reaction on surfaces. We talk about flame and flame propagation, laminar burning speed, effect of turbulence on flame propagation. We talk about the effect of residual burn gases, or EGR, which stands for exhaust gas recirculation, which used to control nitric oxide, on flame propagation. Impact of multiple spark plugs on flame propagation. We talk about cylinder pressure measurements and its behavior and its analysis. Effects of spark timing, advanced retardant on cylinder pressure. We talk about mass fraction burn curve and heat release analysis, which is an important diagnostic tool. Auto ignition, knock and spark ignited engine, physical meaning of a specific heat, and cyclic variability and how it is quantified. So this is kind of a list of some key important terms and concepts that are very important to know. Engine design, in my opinion, is really an orchestrated endeavor by engineers, scientists, mathematicians, managers, and economists to really create a beautiful product. It's as beautiful, frankly, as a symphony. Because all of these components that you see, and there's a complex machine, they have to work in harmony. So we have this marvelous engine that we have these days. Now let's go through the history of evolution of designs of engine. You can see down here approximate years or range of years that a certain design was used. Early on, we had a carburetor. Essentially, you still have to have a device that somehow introduces fuel into the system, and then you have to bring the air and bring them together to start and initiate combustion through some external sources such as a spark plug. In the old time, it was a carburetor, which was an ingenious design, and there was a kind of venturi in the intake system where the fuel is introduced. And then there's the throttle valve here, which is connected to your gas pedal. When you push the gas pedal to the end, essentially this valve is going to be fully open, which we call it wide open throttle, or WOT for short, where you get the maximum power. So the power in this engine essentially is controlled by opening and closing the throttle valve, which limits the amount of air goes into the engine. Then, as the manufacturing technologies and so forth improved, we went, and also electronics, we went into electronic fuel injection system, and this fuel injector has a solenoid inside which can be controlled through electronics and subsequently can naturally be controlled and connected to computer electronic control system. And so carburetor is removed, and you have a fuel injector that is sitting and injected spray into the intake port. And throttle valve is here. You have your spark plug as before. There are many advantages here. We will discuss that during the seminar of doing this. And then people have decided to put the injector, or a gasoline fuel actually, spark ignited engine, instead of injecting into the intake port where the injector sits in the intake port, we inject it directly into the combustion chamber. So here's the injector sitting here, here's the intake valve, and here's the intake port, and here's the spark plug, and the fuel is injected directly into the combustion chamber. This is for short called gasoline GDI, or gasoline direct injection. And here's an example of it, that you can see your spark plug and your injector, and these are valves. And usually the injector is put in the intake side, and as far as the temperature is concerned, so you don't want the injector to get too hot because of deposit issues and operations and so on. Then, of course, we also have diesel engine. We've all had, and this is one of the most efficient engine we've ever had. Efficiencies for large diesel engines goes to 55%. And in this case, you have your injector sitting here. There's no spark plug, and has always been like that, where you directly inject into the combustion chamber. Load is controlled here in diesel engine through the amount of fuel that you inject. There is no throttle valve, and that's one of the big advantages, in addition to higher compression ratio. So then, in the in the gasoline fuel engine, in the past 20 years or so, people have been successful going into what's called HCCI engine, which stands for homogeneous charge compression ignition. This is a combustion mode, technically speaking, but people many times call it the HCCI engine, or nowadays also referred to as low temperature combustion. Essentially, the objective is to capture the goodies of both diesel engine and homogeneous charge, spark ignited. This engine, the ignition is similar to diesel engine. There is no need for a spark plug. Of course, you needed to start the engine and at full power operation, but during the part load operation, you will operate under homogeneous, so your fuel and air is homogeneous in contrast to diesel engine, which is heterogeneous or stratified, and ignition is by compression ignition. So the advantage here is that highest efficiency, and at the same time low emission of pollutants. On account of homogeneous charge, soot is almost out of the picture, particularly if you run lean, and compression ignition essentially means almost a spontaneous combustion, which we're getting close to ideal auto cycle. So the combination increases the efficiency. There are so many things about this, and we will discuss in the seminar as well. And you can see how and why the people are working on this, and tons of money going into that for R&D, and we have prototypes and so on. There are some terminologies. It's understood that many of you taking this seminar have basic knowledge of these terminologies, such as piston and so on. If not, you could go into that. Our focus is going to be mostly here in the combustion chamber. And the four-stroke engine, for example, its operation is going to be is explained here. Well, you bring air, or fresh air, or if you have EGR, it's going to be air, fuel mixed with some exhaust gas recirculation, comes into the engine. The piston is going down during the suction or intake phase. And then you see the valves are closed and you do the compression. And at some time or crank angle before this piston reaches its uppermost position, you ignite, which creates a flame, and the flame propagates and burns the fuel and releases the energy. So it's a really conversion of chemical energy, which is stored in the fuel, into thermal energy and subsequently into mechanical energy, which pushes the piston down. Then we have to send all these burn gases out so that prepare this for the next cycle. And the exhaust valve opens up, all these burn gases first by blowdown, as a result of differential pressure goes up, and then by displacement of the piston. There's some terminologies basic, such as top dead center or TDC and bottom dead center. The lowermost position piston, if it is here, this is called bottom dead center. And the uppermost position is called top dead center. And the volume that it sweeps, we call it, essentially is a displacement volume. And the distance is called a stroke. And the volume that remains when the piston is at top dead center, we call it clearance volume. And this diameter is also called bore. So what is combustion? Well, essentially combustion or burning is a rapid self-sustaining chemical reaction that releases a significant amount of heat. Now there are many examples of it for common processes, combustion processes such as burning candle, forest fire, log fires, the burning of natural gas in home furnaces, and burning of gasoline in internal combustion engine, which is the focus of our discussion here. In order to have the combustion, you need three things that must normally be present. You need a fuel, you need an oxidizer, and an ignition source or a stimulus. Fuel can be, in general, solid, liquid, or gas. Obviously, solid fuel would be tough to use in automotive engine. Examples of solid fuel are filter paper, wood, or coal. Liquid fuel includes gasoline, kerosene, and many others, including diesel. And gaseous would be propane, hydrogen, are examples of gaseous fuel. Oxidizer can also be solid, such as ammonium perchlorate, which is used in space shuttle booster rockets. Or it could be liquid, such as hydrogen peroxide. Both of these two are used in rocket industry. Or gaseous like oxygen, which is used also in rocket. However, air is available and is mostly used in automotive engine, which contains oxygen and is practically is common oxidizer. And the electrical spark is an example of an ignition stimulus. This is just one example. There are many other approaches, lasers and others, which we will discuss that in details on another seminar on the title of ignition. Combustion is really a key element of many modern societies' critical technologies. Electric power production, these are all examples. Home heating, ground transportation, spacecraft, aircraft propulsion, and material processing. All of these really use combustion to convert chemical energy to thermal energy or propulsive force. Now, combustion has been around for years, despite the fact that it accounts for approximately 80% of the world energy usage and is vital to really our current way of life. It poses great challenges to maintaining a healthy environment. Therefore, improved understanding of combustion will help us to deal better with the problems of pollutants, atmospheric change, global warming, unwanted fires and explosions, and incineration of hazardous waste. So the part that we cover on combustion would be useful for many applications wherever you are. Unfortunately, despite vigorous scientific examinations for over a century, researchers still have lack of full understanding of many fundamental combustion processes. Now here, I want to explain sort of ways that we could bring essentially what are the ingredients that are needed to have our combustion. Well, if you look at the bottom here, the question is how fuel and oxidizer are prepared. You know, it could be prepared in such a way that is premixed before starting combustion, or we call homogeneous or premixed, or it could be heterogeneous or non-premixed or diffusion. Then also fluid motion comes into picture, which is important. Now, essentially we have two choices from fluid mechanics perspective. Either flow is turbulent or laminar. In most practical application of interest to us, flow is turbulent. For example, if you come here, and there are examples here, if you have a homogeneous mixture and its turbulence, what are the examples? Well, a spark ignited gasoline engine, low NOx, a stationary gas turbine for electricity generation, other applications. And what about if you have a premixed, fuel and air premixed before combustion, and the flow is laminar? Well, the example is the flat flame burner, Bunsen burner that many of you probably had even in high school chemistry labs. And here's the heterogeneous non-premix, meaning at the time when the combustion starts, we don't have a fully premixed fuel and air. By fuel I mean vaporized fuel and air. If it is turbulent and heterogeneous, examples are many. Aircraft gas turbine engine, hydrogen oxygen rocket engine, space shuttle rocket engine, diesel engine, polarized coal combustion. All of these are under this blend of being heterogeneous and turbulent. Now what about if it's non-premixed and laminar? Well, examples of candle flame, radiant burners for heating, and wood fire. So it's a nice slide in terms of putting everything in perspective, applications, and the two important ingredients, fuel oxidizer mixing and fluid motion. Hydrocarbon fuels classification. Well, there's a table here, a series of slides after this, that the heading of the table is as you see here. First class is the alkyl. And the formula is as shown here. The molecular structure is chain, and whether saturated or not says yes or no. And here it shows you the naming, whether it's prefix or suffix. For example, the general formula for what we call paraffin, which is the subclass here, or alkanes, is CnH2n plus 1. If you put N1, you get CH4, which is methane. So it's a carbon. It's the simplest pure hydrocarbon. By the way, first we're going to talk about pure hydrocarbons. And then once we understand that, this classification, then we go into gasoline fuel, which is a blend of all of these hydrocarbons and more. Now, if we put, for example, C3, then you get propane. So it would be C3H8. Now, molecular structure of propane is like that. This is a carbon. Each line here indicates the sharing of the electron, the bond between carbon-carbon, and carbon-hydrogen. All of this here, there is a hydrogen molecule here, 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 here. But for the shorthand notation, we removed it. So that's kind of customary to do that. So otherwise there are hydrogens all around here. So you see the molecular structure is in the chain, and it's not saturated. It says saturated, it's a yes, in the sense that you cannot add more hydrogen into this molecule. There's just no room to add hydrogen. And there are also two types of paraffin, normal or isomers of any one of these. And you can see an example here, normal paraffin. Here's one example, which is like a chain continues. but having the same molecular formula, but a different structure, such as this. This is an isomer. We call it isoparaffin. This is as a class of the hydrocarbon. So, well, I'll stop here. Just the purpose here to give you a feel of what it is that if you are interested in this, the entire presentation can be purchased. And if you're interested, you could contact Advanced Technology Consultants for pricing and other matters related to that. Thank you.